Today on My Climate Journey's startup series, our guest is Sarah LeMason, CEO and co-founder of Dioxcycle. Dioxcycle is developing technology to produce sustainable ethylene from recycled carbon emissions. Ethylene is the world's most used organic chemical, and it's a precursor to many everyday products, including construction materials, plastics, and textile fibers. Indeed, it's a core feedstock for polyester. I was excited to learn from Sarah about Dioxcycle as an example of a startup leveraging electrolysis to convert electricity, water, and carbon emissions into low-carbon chemicals. Dioxcycle announced a Series A of financing earlier this year with investors including Breakthrough Energy Ventures, Lowercarbon Capital, and Gigascale. But before we dive in, I'm Cody Sims.
I'm Yin Lu.
And I'm Jason Jacobs, and welcome to My Climate Journey.
This show is a growing body of knowledge focused on climate change and potential solutions.
In this podcast, we traverse disciplines, industries, and opinions to better understand and make sense of the formidable problem of climate change and all the ways people like you and I can help. Sarah, welcome to the show.
Hi.
Sarah, I am super excited to learn from you today because I'm starting from a very low base of knowledge when it comes to the world of ethylene, which is the world that you work in, as I understand it. Maybe let's start with a little bit about what is Dioxcycle.
At Dioxycle, we are developing breakthrough technologies to convert industrial carbon emission to ethylene. And so what is ethylene? Ethylene is the world's most used organic chemical, and it's used basically in all everyday products ranging from short life packaging but also like consumer goods, auto parts, different plastics, to long lasting building materials such as PVC piping, high density polyethylene, this kind of stuff. And so right now, the problem with ethylene is that it's a huge market. It's a $180 billion market. And the production of ethylene is associated with a lot of carbon emissions because it's currently made through like steam cracking of fossil resources, which is a high temperature, highly emitting process. In that process, not only you need to extract oil to actually make the ethylene, and so you're contributing over 560 million tons of CO2 equivalent per year of like embedded carbon in the ethylene, but you also need the fuel to actually heat the crackers to make that. And so you're contributing like an additional 240 million tons of CO2 per year. And so in total, basically, ethylene making adds to the surface of the earth like 800 million tons of CO2 equivalent per year, which is like between 1% and 2% of the world's equivalent emissions. So it's a huge problem. And yeah, a lot of approaches have tried and are at some scale right now to actually displace that process. But there is, a lot of hurdle in terms of the economics that these can reach. And so our goal is to make that happen cost competitively and sustainably so that we can really decarbonize that process.
So I'm hearing ethylene is this incredibly abundant material or chemical that is used in the production of lots of things that we touch and use in our lives. It's one of those foundational chemicals of essentially modern society. And today it's made primarily by, I assume, big chemical companies who are buying either oil or are buying natural gas and are then taking the fossil fuel, primarily the oil, I presume the petroleum, heating up a bunch of steam, probably using mostly natural gas to do it, to crack it and create a chemical reaction that ultimately produces this ethylene. Did I follow correctly what you were describing?
You did indeed.
How is this the area that you decided to focus on? What's your background that led you to, we haven't talked about how you're approaching it yet, but what led you to decide this was a problem you wanted to work on?
We founded Dioxycle with David Werkely, my co-founder and CTO, 3 years ago now. And before that, we actually carried out 5 years of academic research together, which takes us to 8 years ago, where we met at the University of Cambridge. And then we worked like for 1 year there, for 2 years nearly in Collège de France in Paris, and then for 2 years at Stanford on like CO2 electrolysis and this field in general, trying to basically reinvent the way we make everyday chemicals, such as carbon monoxide, which is a precursor for jet fuel, ethylene, ethanol, which is another fuel, And so it's really like after 5 years of academic research, trying to understand how these technology could be used to displace these fossil processes, that we decided to found a company, basically.
Is this your first go round as a founder running a business out of the academic research that you've done?
Yes. During these 5 years, I completed my PhD and then did a small postdoc. So yeah, first time founder. I don't want to say it's my first job. I will confess it's also my first job.
How's it going?
It's good. It's hard, but it's good. It's fun.
It's hard. That's for sure. Congrats on making the leap and deciding to take the work that you did from a research perspective and try to turn it into something that can, it sounds like help the world move a big chunk of what we touch and use and access every day into a process that doesn't leverage fossil fuels to produce that thing. We often hear, hey, so much of the built world around us and so much of what we take for granted in our lives is fossil fuel derived that we don't even realize. And it sounds like this ethylene process is one of the major contributors to that today. I'm curious, a few outputs that you mentioned. As I understand it, ethylene is the primary feedstock for polyester. Is that accurate?
Yes, indeed. Polyester fabrics, which is ubiquitous in a lot of clothing, is made from ethylene. So that's also one other interesting area to reinvent based on that novel chemistry.
A question for you, taking the raw chemical that you create of ethylene, or the raw chemical compound, I suppose, what's then the next step, for example, to take it to a finished product, whether it's polyester, whether it's some other material you mentioned, I think a lot of construction materials or other plastics. How do those refinements continue on typically? Are there additional fossil fuel inputs usually in those processes as well?
It depends. If you take the simplest one, let's say polyethylene, then it's just a polymerization starting from the ethylene. So if you decarbonize the ethylene, then you really decarbonize the polyethylene. Then there are like a bit more complex products. For the PET, you have T, which is terephthalic acid, comes from that. And so for this one, you also have to decarbonize this part of the process. But in a lot of these different products, ethylene has a huge weight into the carbon footprint of the final product.
Super helpful. And just a good reminder to everyone listening that, as we all probably know at this point, there's no silver bullet. There's lots of dominoes that need to fall. It sounds like you're pushing over, hopefully, a very large one, but there are additional dominoes around you that other people, or maybe even you in the future, will also likely need to work on as we really look to decarbonize our global economy.
I agree.
Looking at other related materials, you mentioned ethanol. I know that's not ethylene, it's different. What is the relationship of ethanol, which, as I understand it, is essentially an alcohol that has been, over the last decade or two, used as a biofuel, I think, if I'm not mistaken? What's the relationship between ethylene and ethanol?
So you can basically dehydrate ethanol to make ethylene. And so right now, one of the main sustainable avenues to make ethylene is through the dehydration of bioethanol. And so the way you can do this, depending on the geography where you are, what is going to change is the feedstock you're using. The most competitive version of bioethylene is, I think, most of the time, the one that comes from bioethanol derived from sugarcane coming from Brazil. So you have a lot of like big actors, big chemical players who have been developing this kind of processes there. Then, if you're in the US, you're going to start from corn ethanol and dehydrate it again to bioethylene, which is a bit more expensive already than the one from like sugarcane in Brazil. And then if you go to Europe now, you're starting from beetroot in some cases, which is even more expensive. And so you're adding to this green premium that now can range from like 30% to like 100% plus. And so none of them, unfortunately, are hitting the nearly zero mark that this kind of commodity market requires to trigger fast adoption.
Based on that and what I'm hearing, I have in my mind that to some extent, overinvestment in biofuels was one of the challenges of the clean tech 1.0 sort of era 10, 15 years ago. And it sounds like not only was that an attempt to invest in biofuels to generate ethanol as a fuel, but it was the promise of then taking this ethanol and transitioning it into ethylene and using it as ultimately a bio-based plastics replacement, et cetera, of which the economics still to date just haven't wholly worked out. There's a green premium to doing that relative to fossil fuel-based ethylene production. And this is where, as I understand it, Dioxcycle comes in, not taking a bio-based approach to this solution, as has been most of the treaded path over the last 10, 15 years, but rather taking an electrolysis approach and using captured CO2 emissions as your base feedstock. Am I following the thread correctly here?
You are indeed. We are developing a really novel type of technology, carbon electrolysis. And I'm saying carbon electrolysis because there are different types of carbon emission. So we can call them like just carbon oxides in general, like CO, CO2. What our process unlocks is that it can take just these carbon emissions and water and electricity to basically convert these carbon emission back into ethylene, which is a high energy dense form of carbon, because when you go from these carbon emissions to ethylene, you're basically creating carbon-carbon bond and, ripping off oxygen. And by doing that, you're actually basically pumping in energy in that molecule that is now like sufficiently reactive, sufficiently like modifiable so that you can actually do some chemistry downstream of that. And so like what is really unique about us is that we have taken a very integrated approach since the beginning, and we innovate at all levels, because to really reach the energy efficiency point you need to reach to make that cost efficient, you basically have to optimize the components themselves, but also all their interfaces, how they interface, how they integrate together. And so we innovate at the component level, developing super high efficiency catalysts, ultra cheap membranes, which are the central component, but also at the system level on the stack design. It's called a stack, electrolyzer stack. At the more like industrial level, working on ways to basically integrate that electrolysis technology into a plant so that you valorize existing assets, so that you basically optimize the cost efficiency of the overall plant. I realize I went quite deep into this.
That's okay. Let me try to summarize what I think I heard, which is you're saying that what's been unique about Dioxcycle is you've innovated and created IP, I think, at each level, including the catalyst you use, the membranes you use for electrolysis, and ultimately the design of the whole system and how it might plug into an industrial plant. And so you're not necessarily pulling off the shelf components for any of these areas. You're actually developing an end-to-end system that is unique, which gives you a very special place in the market from a technology perspective. Did I follow you correctly there?
It is correct. And I think it also gave us a possibility to like really iterate fast. And we've been developing 3 iterations of stacks so far in less than 3 years, which was a lot of things to pull together.
Interesting to hear you say you're iterating fast when you're having to develop proprietary solutions in each of these areas. I would think that would add a lot more complexity, but I guess it also reduces supplier dependency to some extent. Is that right?
Exactly. At some point, when there was this, it's not as if it was completely finished, but the supply chain constraint, not only on the chips, we were also like doing all our electronics. We were kind of changing depending on what was available on the market, the architecture of our boards, to be able to actually develop the system and make sure we would deliver these kind of prototypes on time. That gave us flexibility.
Can you describe what this electrolyzer looks like? Roughly the size, roughly the shape and the process of how the CO2 gases run through it?
It's called an electrolyzer stack because you're basically stacking individual cells on top of one another. The reason you do that, and you do the same in water electrolysis to hydrogen, is just to basically demultiply the active surface area with the kind of same footprint and the same external component, let's say. And so what you have on the stack is basically you have manifolds that bring in your emission, your input, that is then distributed at the surface of each individual cell. Each individual cell comprising 3 elements: a first electrode that converts that to ethylene in our case, separated by a membrane that allows like ion transports, from a second electrode that is converting water to oxygen. At the end, let's say, of this active surface area, you have your output stream containing that ethylene that goes out from your stack on one side, and on the other side, you have your oxygen also in a separated stream, which is interesting from like some chemical application as well.
And the CO2 gases that your assumption is the chemical plants are leveraging, are they typically coming from what you expect to be captured CO2 emissions from their own operations and other parts of their chemical processes? Or do you think most of them are buying industrial CO2 from somewhere and piping it through your system?
It's hard for me to completely answer to that because right now, the first 3 years really developing this medium scale stack in-house and really proving that this technology can reach the performance we want it to validate so that it brings forward this unique economic value proposition. And now we are actually at that pivotal moment where we have raised that Series A in July, led by Breakthrough Energy Venture, Lowercarbon, and with Gigascale Capital, to actually deploy our first industrial pilot.
You're trying to figure that out, yeah.
Yeah. We have some things, don't worry, but we are actually now in that phase of assembling the full value chain from the capture to the utilization to the downstream purification of the ethylene so that it can be reused on site or actually sold to a third party depending on the type of emitter you're basically plugging that system.
Hey everyone, I'm Yin, a partner at MCJ Collective, here to take a quick minute to tell you about our MCJ membership community, which was born out of a collective thirst for peer-to-peer learning and doing that goes beyond just listening to the podcast. We started in 2019 and have grown to thousands of members globally. Each week, we're inspired by people who join with different backgrounds and points of view. What we all share is a deep curiosity to learn and a bias to action around ways to accelerate solutions to climate change. Some awesome initiatives have come out of the community. A number of founding teams have met, several nonprofits have been established, and a bunch of hiring has been done. Many early-stage investments have been made, as well as ongoing events and programming, like monthly Women in Climate meetups, idea jam sessions for early-stage founders, climate book club, art workshops, and more. Whether you've been in the climate space for a while or just embarking on your journey, having a community to support you is important. If you want to learn more, head over to mcjcollective.com and click on the Members tab at the top. Thanks, and enjoy the rest of the show.
And are you hearing from chemical companies that there are certain parts of the ethylene process that are wanting to replace today, meaning ethylene that is going to a certain destination or being turned into a certain compound is the first area they want to start? Or are they just looking to change their process regardless of how they produce ethylene in the first place?
There's now, thankfully, a global understanding that we need to decarbonize this kind of, hard-to-abate sectors in general. I believe everyone is looking for an economically viable way to decarbonize this kind of production, regardless of the downstream uses. Of course, there are some more niche markets where there's some possible green premium. Actors who have been scaling up technology to make sustainable ethylene have been focusing on at first. But overall, the chemical industry is actually right now just looking for a way to simply decarbonize their process viably. And I think one thing that has been done recently by, I think it's Dow in Canada, to actually start doing this at large scale is to, when you have your cracker, if you have already built a cracker, that's a huge asset. And so what they have announced recently is that they will replace the fuel that is used to heat the process by hydrogen so that you suppress the process emission part of that cracking. However, even if you're doing that, if you remember the numbers, it's 1/3 of the carbon you're adding to the surface of the atmosphere that you're now suppressing because you still need the fossil resource to extract it to actually provide the carbon content that is then embedded in your ethylene. From a, let's say, scope 1 emission for that plant, that's definitely a solution. But for a scope 3, for all the downstream users, there is still a part that is not decarbonized by doing this.
I'm hearing you say that the trade-off that these chemical companies are having to look at is, hey, we maybe have already invested significant capex into both the cracking process of the hydrocarbons that we use, the fossil fuels that we use. What parts of that should we look to decarbonize? Well, if Dioxcycle didn't exist, they might be looking to put carbon capture and storage solutions, which also, by the way, aren't fully production ready yet, but are getting there, onto the part of the process that they need extreme heat for to generate the steam necessary for the cracking. And so you can maybe capture the emissions off of the heating element, which is about 1/3 of the potential emissions from the chemical process. But then you have the chemical process itself of cracking the fossil fuels, which is going to be roughly 2/3 of the emissions released from this process anyway. Did I follow what you just said?
I think you said the same thing, but just to make sure, the 2/3 I'm talking about is the embedded carbon, basically the carbon content of the ethylene. If you consider its end of life, will be re-emitted unless it's recycled. And so that's the part that is not decarbonized, but by electrifying the crackers or by using hydrogen, they manage to drastically reduce the process emission.
Oh, I see.
Yeah, but the process emission should be kind of okay.
So it's the embedded emission because fossil fuel was the actual feedstock of this thing. So as it lives its life, it still has emissions in it to some extent.
Yes, exactly.
Even your green produced ethanol obviously still has carbon as a element in the ethanol itself, does it not?
Yeah, of course. There's no magic formula, I mean, you have to source the carbon somewhere. So there's always this question of carbon accounting. If you are growing corn or sugarcane, this carbon is considered neutral in itself. Then there might be like full life cycle analysis where you take into account land use, fertilizer, all these things, but like the carbon itself is considered zero, carbon neutral, contrary to like the fossil type of carbon. So that's where there is this difference of treatment, of course, between the fossil and the biocarbon, because at least the bio was like already at the surface of the earth. You're not extracting more and adding to the surface of the planet.
That totally makes sense. So taking the inputs into account, you're not creating net new demand on additional fossil fuels to be drilled and explored in order to create this process. And as I understand it, today, the chemical value in a barrel of oil is fairly significant. I can't remember, it's 20, 30, or 40%, like somewhere in that ballpark. A significant chunk of the barrel of oil is the chemical value from it, not the fuel value from it, for example. And as the world weans itself off fossil fuels, if we don't in parallel wean ourselves off chemicals, presumably oil will still be extracted from the earth to continue to feed these chemical processes. And the fossil fuel industries are only going to become more reliant on the chemical industries as a source of revenue for them over time, one could assume, if we don't start to move the chemical processes as well to being fossil free in nature.
Completely agreed.
Great. Okay. Help me understand the relative then impact that you believe you can have. You say that you'll be not a green premium. Is it presumably cost competitive or even cost discount to existing processes, not, of course, factoring into whatever embedded cost or loaded costs they may already have in terms of CapEx investments?
By basically combining the different innovation I mentioned before on the component like membrane, electrodes, stack design, process integration, we are really targeting a cost point below these fossil prices. So we are really talking here about a potential negative green premium. We need to do that at full scale right now. It's always hard to fully validate that until you have a plan running. But I think the simplicity of that process and the CapEx reduction due to how straightforward it is, and the OpEx reduction due to the increased energy efficiency versus best other sustainable alternative takes it really to that green discount and, in the worst case, zero green premium type of category, which I don't think has been out there before. So that's quite exciting. When we do all our cost projection, we really look at a world without even any carbon incentives, because we're like, let's plan for the worst. If there was no carbon incentive, what would happen? And we would still need to incentivize the transition. And so, for geographies that don't have a regulatory framework that is incentivizing that, does it still work? And it does. So that's the important part of the value proposition that we are really building through this novel technology.
You're talking about government subsidies for production of these materials?
Yes. Of course, that helps. That definitely helps. That helps even just in going down the cost curve at the beginning when incentivizing the CapEx investment for like commercial demos of their kind plants. But in the long term, our goal is really to manage to have this value proposition without regulatory incentives.
As you look toward where you might commercialize, do you have a sense that chemical companies are in the process of managing replacement cycles and actually moving away from existing CapEx that they might already have in fossil cracking and whatnot to generate ethylene? Or are we seeing entirely new efforts to build new plants and new processes from the ground up?
Right now, because there's not many sustainable alternatives which are cost competitive, we are not seeing a lot of things. I think what has been seen is that, for example, in Europe, there is one cracker that has been opened for ethane cracking instead of naphtha cracking, because naphtha cracking emits like 1.7 tons of CO2 per ton of ethylene, whereas like for ethane cracking, you're more like on the 0.9, 1 ton of CO2 per ton of ethylene. So there's this first optimization of the process with like a better resource, let's say, in terms of the process emissions. For now, there are not a lot of big plans for these kind of things, apart from the bioethanol dehydration type of efforts. But I'm not at least aware of like so many plants using completely new processes to do this. One avenue that is looked at by the chemical industry is methanol to olefin in Asia, because they already do methanol to olefin, methanol to ethylene and propylene. But usually, they started from coal. So they would take coal, gasify coal, get a syngas, and then do like methanol, make methanol, and then do methanol to olefin. Starting from coal, the economics makes sense for this process. If you now want to make green methanol, which is, already much more expensive than, let's say, gray methanol, and then do that, you're really adding on the stack of costs there. And so that's one avenue, because at least the methanol to olefin process is at scale, but it's probably not realistic for a lot of geographies to look at this one because of the cost it's going to take. And you also need huge scales. So I would say right now there are not so many options. I can cite other avenues. For example, you also have, of course, the Lancetite process, which is doing conversion of carbon emission to ethanol, and then they can dehydrate that ethanol to do ethylene. They have done a lot. I have a lot of admiration for this company who has been doing these kind of processes for a long time. They are building plants. I do believe that the economics are tough there as well. So it's a really complicated field to decarbonize, especially when you think about the volumes we are talking about. It's so crazy as an industry.
It would seem like, in addition to looking at your solution and deciding, I want to try a pilot of this, or I want to work to see if this would be a pathway to decarbonizing my ethylene production as a chemical company, these chemical companies also are going to have to build competencies, presumably in power purchase agreements and accessing renewable power. Because again, today they've mostly been pulling chemical power on site, whether that's direct natural gas or other fuels that they're using for the heating and cracking process. But in your electrolysis-based process, it's just electrons. To some extent, they're going to want to also ensure that they're using renewable power to power your process. Is that correct?
It is completely correct, indeed. When we decided to incorporate the company, we first came to France. Now we are, between France and the US, but we first came to France because it had a very decarbonized grid because of all the nuclear power that is installed. It's what really makes the carbon footprint reduction of the process. So you really want to go towards the most decarbonized power source possible. And so PPA with dedicated project, renewable project is definitely a really good way to go. And then once you have that, you have to then think about the capacity factor. So how many hours in the day you can use that, or how resilient this kind of process is to intermittency. It's an advantage of the type of low temperature electrolysis technology that we are developing. You have far less heat inertia compared to other high temperature, for example, hydrogenation processes. So that's one very good thing where it makes it really suitable for this kind of coupling with renewable electricity, which hopefully will drive the carbon footprint even as low as possible for these kind of processes.
Yeah, and it's just a good reminder that for anyone listening who's trying to build your own personal competency in being a power purchaser or in helping companies understand their own sustainability transformations, these skill sets around how to procure and acquire renewable power are being applied to all sorts of different kind of companies today. And most of them are building these skill sets relatively fresh, just because the way they've done things in the past and access to whether it's natural gas or other sources of energy to power their processes or power their way of doing business is likely shifting. What do the next few years look like for you? You mentioned you've raised the Series A. You're now getting to the point of trying to get an end-to-end process in production from a pilot perspective. What are you going to be spending most of your time on?
We raised our Series A in July. And so the next 2 years are going to be dedicated really to the final design, deployment, and demonstration of that first industrial pilot, which will be the final size of our electrolyzer stacks. Very exciting, actually, because then 2 years down the line, it's the right form factors to prove what you want to prove in terms of the core of the process. And so the idea is to put it on site with the adequate balance of plant to actually really go from the capture of the emissions, as I mentioned, to the conversion to the downstream purification of the ethylene to demonstrate its viability for different type of downstream processes and different type of downstream industry. So very excited by that. So with that in mind, our goal and biggest focus right now with Dave is really to assemble that next layer of the team, bringing in much more industrial expertise in the team. We already have a great combination of industry and academic profiles, but we have really spent the first 3 years solving scientific problems. So our team composition has reflected that need. And so our goal now is really to expand on, the process team, the finance team for project finance questions and all these things that are going to be so key in building the monetization model of our solution so that once this pilot is done, we can really go with a sort of packaged offer to our customer and say, okay, this is how it's going to work. This is what you're going to pay. And that's the full offer from an environmental and an economic perspective. So that's the focus.
Roughly, how do you expect the business to make money?
We expect the business to make money through model of provision of technology, either owning and operating the CapEx ourselves. And so then we do all the financing of that project or selling the CapEx. I'm mentioning these two models because right now in the gas industry, for example, when you need oxygen on the site, the major gas management can do these two different models depending on the sort of business culture of their clients. So either they sell them the full equipment or just this offtake agreement, long-term purchase agreement of the product they are making on site to make sure they will have a return on this plant and do the investment themselves. So we are really seeing ourselves in a similar fashion as these kind of technology providers.
That answer would then impact the next question I was going to ask, which is how you expect to finance each of these plants. Is it project financing relative to the customer that you're working with, or do you raise dedicated financing? I guess it depends on if they're just buying the CapEx from you. It's a co-development with the customer, I guess. Otherwise, if they're just buying the material from you, then presumably you need to raise project financing to build the facility yourself.
Exactly. That's why one of my first recruitment right now is going to be about this profile. We are recruiting a head of finance with that sort of dual experience in startup and project finance to bring in that knowledge because I'm not an expert. What matters in our case is that we kind of completed the first task, which is make sure the P&L works, which I think is already very big. So we did this and now we're whoever bears that CapEx is going to work out. So we just have to do all the machinery of the payment package there.
Where are the big ethylene production centers in the world today? I'm going to assume Texas.
Yes. In Europe, you have all the Antwerp kind of region. You have huge plants in the Houston area. You have some in Canada as well. I mean, they're pretty much everywhere.
Presumably relatively near large oil and gas centers.
Exactly. Or next to some places that are easily accessible through sea so that you can actually get that feedstock for the process.
I saw on your website you have a vision of Dioxcycle being the Intel inside of CCUS, or in other words, the trusted tech provider to empower chemical manufacturers to reinvent chemical processes based on emissions recycling rather than fossil fuel extraction. Describe that. How do you view the company evolving over time?
We know our strength. Our strength is really the technology side of it. When I say the technology, is the CC, particularly the utilization of this emission part of the technology. And so our goal is to really double down on these strengths, and we will not become an actor on the compressor manufacturing. That's what we kind of mean through that sentence. And we really want to build that brand around the quality and the efficiency and the CapEx efficiency, energy and CapEx efficiency of the system we are building. And that's what we are trying to reflect in this sentence. Because at first, as I said, we are going to have to make all these plans ourselves, and we will continue to do that forever. But at some point, to also accelerate the adoption of this kind of technology, we think about having a second type of like deployment model, which is through additional licensing to engineering companies. As the ecosystem develops, there will be more and more projects. So more and more people who will also be able to actually develop this kind of project and this kind of technology that are just nascent. And so at that point, what will keep differentiating us is the quality of the core technology. And that's our focus in the long run.
Sarah, you mentioned needing help in the area of finance and project finance. Are there other areas you're currently looking for assistance for any listeners who are intrigued by what you're doing?
Yeah, we are looking for a head of process engineering as well. Very exciting role, especially now we are like working on these pilots. We are already have like process engineering profiles, but adding a very senior role to that team. And we are also looking for good electrochemists in the Bay Area, where we have a lab very focused on the development of these electrodes. And a lot more on the career page.
And we didn't hit on geography, but you are in Paris and the San Francisco Bay Area as your two main offices. Is that correct?
It's correct.
Great. Well, Sarah, anything else I should have asked or anything we should have covered that we haven't talked about today?
Well, I think one thing we can add is the first answer to climate change is sobriety. I am a strong believer taking less flights, eating less meat, doing all these things that as a citizen we can do. And the International Energy Agency tells us that by 2050, 5% of the emission reduction will be achieved through that sobriety as the first step. And so I think that's an important thing. We are only making a technology that has the potential to revolutionize a chemical process, but it's only one chemical process. And there's so much more we need to do. And we are so many people capable of doing so many things collectively that I think it's very important that we don't wait for the technology to actually really try and transition.
Well, that's a nice sentiment to end on. And I appreciate you for joining us and staying up late in Paris to hop on this podcast. I'm sure our listeners appreciate it too. Thank you, Sarah.
Thanks a lot, Cody. Thanks for having me. It was such a pleasure and an honor. Thank you.
Thanks again for joining us on the My Climate Journey podcast.
At MCJ Collective, we're all about powering collective innovation for climate solutions by breaking down silos and unleashing problem-solving capacity.
If you'd like to learn more about MCJ Collective, visit us at mcjcollective.com. And if you have a guest suggestion, let us know that via Twitter at MCJPod.
For weekly climate op-eds, jobs, community events, and investment announcements from our MCJ venture funds, be sure to subscribe to our newsletter on our website.
Thanks, and see you next episode.